Hello everyone. Today I will begin a new class called Point Set Topology. In this class, I will talk about the different concepts related to topology, topological space, and open sets. So in the first class, I will talk about the topology, what is topological space, and what is open sets. So at first, let's look at the definition of topology. So according to the definition, a topology on a set X is a collection T of subsets of X having the following properties. And there are three properties here. So this sentence means that the topology is a collection called T. So what is collection? The collection is actually a set, but it is different from an ordinary set. Collection is a set of sets. So for example, because the topology is a collection T on a set X, so if we have a set X here, and we have a collection T, and we have elements A and B are the elements of the collection T, then those A and B should be sets. And here we know that the collection T are the sets of subsets of X. So the elements A and B of the collection T should be subsets of X, like this. So those two subsets of X should be the elements of T. But the problem is that we don't allow all the subsets of X to be the elements of T, because we need to give the topology a special property. So we don't allow all the subsets of X to be in T. And those properties are listed here. There are three properties. So if the subset of X satisfies those three properties, then they can be the elements of the topology T. And the three properties are like this. The first property is that the empty set and the entire set X are in T. So it means inside the collection T, we have the empty set, and the set X, the entire set X in the T. And we know that for any set, the empty set is always a subset, and the entire set X is a subset of the set X itself. So for any set X, we can always have those two subsets, and so that we can always have two special elements in the T according to the first property. And so this first property allows us to have two special elements in the topology, and then we can use them to do some special things. And the second property is that the union of the elements of any subcollection of T is in T. This means that if we do the union operation over any number of elements in the topology T, then the result is still inside the topology T. For example, if here A and B are the elements of T, A, B are the elements of T, then the union of A, B, let's call it C. This new element C should also be an element of T. So this second property ensures us to make sure the union operation is closed under the topology is closed under the union operation. It means that we, like every time we do the union operation for the elements of T, then we can ensure the result is still inside the T. So this property allows us to use the union operation freely in this topology T. And the third property is similar as the second one. It says the intersection of the elements of an infinite subcollection of T is in T. So also, if it means that if we do the intersection over some elements of the T, the result is still in T. So, for example, A and B are the elements of T, then the intersection of A and B, let's call it D, and this D should also be an element of the T. So, this third property also allows us to use the intersection operation inside the T without worrying the result to be outside the T. So the T is closed under the intersection operation. But there is one thing we should note is the intersection can only be performed over finite many elements of the T. This is because the topology T is the elements of the topology T are the open sets, and we will talk about this later. And so we can, according to our previous knowledge, we know that the intersection of open sets not always open set. For example, if we do the intersection over finite many open sets, we can always get a open set at the end. But if we do infinite many intersection, then the result might not be an open set. So that is why we limit the intersection over finite many elements of T. So those are the three properties that the subsets of X should be satisfied to in order to be an element of the topology T. And okay, we can look at an example about the topology. For example, we have X. The X has the element A, B, and C. Then we have a collection T like this. We have A. We have a set of A, a set of B, C, and a set of A, C. So the question is this collection T a topology of X? So in order to determine if T is a topology or not, we should use those three properties to verify the elements of T to see if the topology T satisfies those three properties. So for the first property, we know that the empty set and the entire set X should be in T. But here we can see that there is no empty set and there is no entire set X. So the first property is not satisfied, and the T is not a topology. And so what can we do is to modify this T by adding those two elements in it, and like this, we call it T prime, and we put empty set in it, and the entire set in it, and repeat the previous elements. I see. Okay, so this new collection T prime it satisfies the first property because the empty set and the entire set X are the elements of T prime. Okay, and so the first property is satisfied. Then how about the second one? So can we, in order to satisfy the second property, we need to determine if we can do the union operation and get a result is also an element of T prime. So for example, if we do the union of the empty set and the X, the union will be X. Then we get then X is in the T prime, so this is right. And how about the empty set with A? So the union of empty set with A is still A. So this set A is still an element of T prime, so it is still inside the T prime. So it works. And let's see, how about the A and the BC? The A union with BC, we get A, B, C, and this is just the X, like this X. So we have X here, so the result is still an element of T prime, so it is no problem. And I think if we check all the possible combinations, possible unions, then we can always get the result is an element of the T prime. So the second property should be satisfied. Okay, and next, how about the third property? So if we do the union over any elements in the T prime, can we get an element as can we get an element of T prime as a result? For example, if we do the intersection of empty set with any other sets, we get the empty set, and it is in T prime. If we do the intersection of X with other elements, we get the other element back, then it should be in T prime. Like we can have an example. For example, if we intersect X with A, the result is A itself. So it is still in the T prime, so no problem. And let's see. Okay, so how about this one? If we intersect the set BC and the set AC, BC intersect AC, then the set should be a set with one element C. Is this inside the T prime? No. So we get an element which is not in the T prime. So the third property is not satisfied. So what can we do is put this element in the T prime. Put it here. So now we have a new element, and the intersection of those two subsets is inside the T prime now. And how about other intersections? I think if we try all possible intersections, we can get an element from T prime now. So I think the third property is satisfied. And by satisfying those three properties, the T prime is the topology of X now. Okay, so this is a definition of topology. Next, let's look at what is topological space. It says that a set X for which a topology T has been specified is called a topological space. This means that if we have a set X, for example X, and we give it a topology T is a topology of X, then we call this set X with this topology T a topological space. So it means that if we have only a set X, it is very tedious or very trivial. We cannot do a lot of things over a set X. And then we use the three properties above to build a topology T for the X. And this topology T will give this set X a special structure and make it into a space. So we call this X with this special structure T, we call it topological space. So that is what is topological space. It is very simple, right? Okay, we can have an example. For example, we can say here we have we can have the set X like this, A, B, C, and the topology T prime is empty set, and set X, set of A, set of BC, set of AC, and the set of C. This is a topology of X, and then if we consider those two things together, the set X with its structure topology T prime, we call this this combination, we call it the topological space X. So this is what the topological space is. Okay, next is the concept of open set. So it means that if X is a topological space with topology T, we say that a subset U of X is an open set of X if U belongs to the collection T. Okay, so it's very simple. Open set. What is open set? According to this sentence, this statement, we know that in order for a set U to be open set, you need to do two things. The first thing is that the U should be a subset of X, right? At first, you need to be a subset of the X, then you can be open set of X. So, and the second requirement is U should belong to the collection T. So U should be an element of the collection T, and that means U should satisfy the three properties in the definition of the topology T. So with those two requirements, a set U can be an open set of X, an open set inside of the X. Okay, so let's look at an example. For example, if like in the one-dimensional line, we have like interval looks like this, and this line is like all the points on this line like forms the set X. So this line is the set X, and there is an interval inside this X. We call this interval U. Okay. So in order to have this U to be the open set inside the on this line X, we need to first U should be a subset of X. So the U should on this line X, it cannot be like here or other place. It should be inside this set X. Secondly, U should belong to the collection T. So if there is a topology T of X, then the U should be an element of the T, and U should so that the U should satisfy those two properties of the topological space and topology. Okay, that is the elements of that is the open set of the set X. So this definition also means that all the elements of the topology are open sets. So that the topology is actually a collection of all the open sets of X, or you can consider that the collection T defines what is open sets of the X, because if you want to have a subset to be open, you need to you need to ensure that set is an element of T. So the topology T is just like a standard for the subset of X to be an open set. So that is the relationship between the topology and the open sets. Okay, so this is the concept of open sets, and that's all I need to talk today. And I hope you like it, and see you next time. Goodbye.